So we are doing today real life examples of quadratic functions. Real life examples of quadratic functions. If you're at home, we're taking the notes in an Algebra Nation workbook. You can go to Algebra Nation and download the workbook if you have a printer at home, and then just print the pages that you need. If you happen to be like on quarantine or whatever, not going to be back for several days, I would do that to keep up, for sure. If you're just out for the day, you can just get your workbook for me when you return, okay? All right, but in the Algebra Nation workbook, these notes come from starting on page 79 from the course workbook, not the practice book, but from the course workbook, all right? It's from section 4, topic 1 in Algebra Nation. All right, so technically this section went with our last module, but I kind of thought it would work better in the module that we're starting now since we just took our test, and I thought it would work better in this module, okay? So that's what we're doing. All right, real life examples of quadratic functions. What can be said of the rate of change of a linear function? Y'all know rate of change is like the slope, right? And we know with a linear function, the rate of change is always constant. Jessica. Always constant. A line increases or decreases at a constant rate. If you have a line, any 2 points on the line are going to have the same rise, the same run, right? No matter where you look. So how is the rate of change of a quadratic function different than that of a linear function? Well, we know the graph of a quadratic is a U shape that either opens up or down. Am I right? Do you think the rate of change for a quadratic function is always constant? If I pick 2 points on this parabola, is it going to have the same rate of change as if I pick 2 different points on the parabola? No, it's not. So we would say that it says, how is the rate of change of a quadratic function different than that of a linear function? Well, they're not constant. Not constant. This next little section, you will see something similar to it on your homework assignment for tonight. Which of the following are examples of a quadratic function? Select all that apply. So basically, if we read it and it sounds like the rate of change is constant, then it's linear. If it does not sound constant, then it's quadratic in these examples, okay? So a car is driven at a constant rate of 55 miles per hour. The graph shows the car's distance over a specific time. Is that quadratic? No, it said a constant rate of speed, right? So that's going to be linear, so we're not going to check that one. A water balloon is dropped from a 3rd floor balcony. The graph shows the balloon's height over the time period after the balloon is dropped. Is that constant or not constant? It is? What do we learn in science? What happens as you get closer to the ground? It gets faster. So is that water balloon going to be traveling at the same rate of speed? No. So is it constant? No. So we would call it a quadratic. So we're going to check that box. A quarterback throws a football. The graph shows the football's height over the time period after the football is thrown. Yeah. Again, that's not going to travel at the same rate of speed, the constant rate of speed the whole time, right? A class is taking a field trip to see Les Miserables. The student ticket price is $10. The graph shows the total cost based on the number of students attending. So if 1 student attends, it's $10. If 2 students attend, it's $20. If 3 students attend, it's $30. If 4 students attend, it's $40. Is that constant or not constant? That's constant, right? It's increasing $10 per 1 student, $10 per 1 student, $10 per 1 student. So we will not check that one. A diver jumps from a high dive platform. The graph shows the diver's height over the time period after he jumps. So usually like you spring, you jump up, then you go down. Is that going to be constant rate of change? No. No, so we check it, right? Because we're checking quadratics. And we have a question about that? Michael and Jessica, please sit up. Okay, right side. A quadratic equation is used for a free falling body where any effects of air resistance are ignored and the coefficient for the quadratic term is constant based on the gravitational force of the Earth, okay? So quadratics are used a lot in science when we're talking about gravity, but like it said, it ignores any air resistance. So like if it's windy or whatever, this is just assuming that it's no air resistance. Say it again? Oh, yeah. All right. So if you see -16, if that is your coefficient of your quadratic term, that tells you that you're dealing with feet. Dealing with feet, okay? So if your A is -16, you're dealing with feet. If your A is -4.9, that tells you you're dealing with meters. Your gravity, the A coefficient of your quadratic term, that's your gravity. When we're talking about with gravity problems, it's either going to be -16 or -4.9. Quadratics aren't always about gravity because you're like, we've done a lot of quadratics where A wasn't -16 or A was -4.9. True. This is just when you're talking about gravity, okay? Your coefficient of your linear term, that is your initial velocity. Don't know what that means? It's kind of like the speed. Yeah, it's like the speed. And your constant, that is your initial height. Okay, that's your initial height. Okay. Also, in the homework, one of the questions, like it'll say like, what does the coefficient of the quadratic term represent? And I realized in my other classes that we still don't know what coefficient means. Coefficient is the number in front of a variable, okay? Quadratic is talking about the term where the variable is being squared. The linear coefficient, that's talking about the term where your variable is to the first power. Constant is the term that does not have a variable. So this is gravity, is that your quadratic term? Your initial velocity, the plus bx, that's your linear term. And your initial height is always the constant. Remember, constant, there's no variable. So when y'all come asking me when you're doing the homework, what does this mean, the coefficient of the quadratic term? And I look at your notes and you didn't write this down? What do you think I want to say? All right, suppose a volleyball player serves from 1 meter behind the back line. If no other player touches the ball, it will land in bounds. The equation h equals -4.9t squared plus 3.28t plus 1.7 gives the ball's height in meters in terms of time in seconds. Okay, we can infer several things about the situation by looking at the quadratic function that models it. From what height was the ball served? Your quadratic term's the gravity, 1.7 meters. The constant is your initial height. So obviously, when you have a volleyball player, they usually don't lay on the ground and serve the ball, right? They're usually standing straight up, holding the ball, and then they serve it. So that initial height was 1.7 meters from the ground, wherever the ball started before they hit it. Okay? So 1.7 meters. What was the initial velocity of the ball? 3.28 what? Meters per hours, minutes, seconds. What do we got? It's in seconds. So velocity is a speed. You want to say per what? So 3.28. Sorry, I can't see that. So much lag time when I record and it makes me crazy, but there's nothing I can do. 3.28 meters per second. I have also posted in Schoology the Algebra Nation video of Amy doing this exact same lesson. I posted that one, and I'm going to post this one. So if you just don't get it, you have two options of the exact same lesson. Okay. Everybody cool so far? And also, if they didn't tell us it was in meters, we would know it was in meters because the quadratic term is negative 4.9. And if we see that, we know we're dealing with meters. If it was negative 16, we would know we'd be dealing with feet, right? Okay, any questions so far? Next page. Since we can also gather information about a quadratic function by looking at the graph, okay? So this is a graph of a quadratic. The time is on the x-axis, the height is on the y-axis. Notice it's not a full quadratic, right? Because if we were to see the rest of the quadratic on the left side, that would be where time is negative, and well, you can't have negative time. So that's why you don't see the whole entire parabola. So let's just talk about what each of these things mean. So box 1, that is your, it says box 1 is your initial height, right? On the graph, that's also your y-intercept. So if you are looking at the graph of a problem, and it's a gravity problem, or any, well, if it's a gravity problem, your y-intercept would tell you the initial height of whatever the object is, okay? If it starts on the ground, then we would know that would be a 0. Box 2, your vertex, that's your vertex, and your vertex tells you where the maximum height of the object. Maximum height of the object. That's what your vertex tells you. Zoom out a little bit. Your axis of symmetry, that is the line where if you folded the parabola in half on that dotted line that I just drew in, that would make the left side and the right side, it'd make it symmetrical, right? And the axis of symmetry, if you look to where your axis of symmetry meets the x-axis, that can tell you how long it takes from the time the object leaves its initial point, how long it will take it to get to its maximum height. Okay, so how long it takes object to reach maximum height. And then box 4, that is your x-intercept. And that's going to tell you how long it takes the object to reach the ground, okay? Because box 4, whatever time this is at, will have a height of 0. Well, 0 is ground level, okay? So box 4 will tell you how long it takes the object to reach the ground. Julio? All right, right side of the page. The following graph represents the height over time of a water balloon being dropped from a third-story window. So, okay, here's the thing. A lot of kids get confused and they think that the path of the graph is the path of the object, okay? If you stick your hand out a window and you drop a water balloon, is it going to go straight down or is it going to like curve out like in this graph? It's going to go straight down, right? Well, a lot of times I can see how it's confusing because let me go back to the left side of the page. If I throw a football, probably would not go as high as it is on this graph. But if you throw, if a football player is standing here at 1, they throw a football, and the football generally goes up, and then it doesn't go straight down, right? It keeps going farther as it continues going towards the ground or whoever's catching it, right? So a football kind of does follow that path. But however, this is not a graph of the path of the object. It is a graph of the height of the object over time. A lot of kids get that confused. So let's go back over here. And let me write that down and let you write that down. The graph is not the path of the object. The graph represents the height of the object over time. Okay, first question says, from what height was the water balloon dropped? What is it? Looks like 25 feet, right? Your y-intercept is your initial height. It looks like it's right in between 24 and 26, and it says in feet, so 25 feet. After how many seconds does the water balloon hit the ground? How much? 1.4? Is that what I heard? Okay, so we know the y-intercept tells us how long before the object hits the ground. So it's between 1 and 2. So this is about halfway. So we're going to be estimating here. I'm going to go with approximately 1.2 what? Seconds. Of course, I want to label that. So those little squiggly lines mean approximately. If you put 1.3 and I put 1.2, that's okay. It's approximately, right? We're estimating, right, Lakin? Head up, please. Is everybody cool with that? At what time, it doesn't ask, but at what time was this water balloon at its maximum height? 0 seconds, right? And they didn't throw it up. It started at its maximum height and then it was dropped down. Okay, next page. Suppose a rocket is launched from a platform. The equation h equals negative 4.9 t squared plus 200 t plus 25 gives the rocket's height in meters and terms of time in seconds. What was the initial velocity of the rocket? 200 what? Meters per second. Velocity, you have to give me the, is it feet? Is it meters per what? Minutes, seconds, hours? So 200 meters per second. Yes. Yes. I'm going to start handing out lunch detentions for heads going down, all right? Heads need to be up. Shouldn't have to keep asking. Oh, okay. From what height was the rocket launched? 25 meters. The initial height is 25. It's in meters, 25 meters. Very good. And we know that just by looking at the equation. And of course, negative 4.9, that's our That is our gravity, and because it's negative 4.9 and not negative 16, we know it's meters, even though they told us it was meters, but if they didn't, we would know because it's negative 4.9, right? If we measure the height in feet, how would the function change? What would be the gravity coefficient? What's the gravity coefficient going to be if it was changed to feet? Negative 16. And would 225 change as well? Yeah, because they're both currently in meters, and they would need to be converted to feet. So we would have to do those conversions, which we don't have to do. Thank goodness, because I am not great with conversions, even being a math teacher. So we would ask Lakin. All right, so the coefficient of t squared would change to negative 16, and the other numbers would also need to be converted to feet. Good job, Lakin. Coolio? Okay, so we should go pretty fast from here on out. It looks like we still have a lot more notes to do, but they go fast, okay? All right, second side of page 82. The following graph represents the height over time a ball tossed into the air from a first-story balcony. From what height was the ball tossed? 10 feet, right here. It's your y-intercept, right? 10 feet. That is your initial height. What was the maximum height of the ball? 28 feet. You can find that at your vertex. 28 feet. How long did it take the ball to reach its maximum height? About what? 1.3 seconds. It did not say how long it will take to hit the ground. It said how long will it take to reach its maximum height. So the maximum height was at 28 feet. And that looks to be, I'm going to say, yeah, approximately 1.3 seconds. If you said 1.3, 1.2, cool. It didn't ask, but how long does it take the ball? Is it a ball? Yeah, a ball to reach the ground. Yeah, about 2.8, right? Approximately 2.8 seconds to hit the ground. So is everybody kind of getting the feel and understanding of what the parts of the graph represent when you're talking about gravity of an object? I hope so. I'm not doing your resistance. Okay, beat the test. Beat the test. A ball is tossed in the air with an initial velocity of 12 feet per second from a height of 5.5 feet. Which of the following equation represents the ball's height in feet over time t in seconds? Look at your options. Which ones can we rule out just right from the beginning? A and D. Why A and D? Because these are in feet, so we know that your quadratic term should be negative 16, right? And on A and D, the quadratic term is not negative 16, so it can't be either of those. It's got to be either B or C. Which one is it? B does not have the velocity, and we know the velocity is 12 feet per second. Well, C has the velocity as 12 feet per second. C is in feet because we see that our quadratic term is negative 16t squared, And C also has an initial height of 5.5. So yes, C is the correct answer. B does not have an initial velocity. If we don't have an initial velocity, it's not a gravitational problem, right? Everybody understand that? And I even color coded it for you. Second half of this page. Consider the following diagram that represents a projectile fired from a cannon from the roof of a high-rise building. Okay, I don't know who wrote this problem, but I do not recommend anyone firing a projectile from the roof of a high-rise building. Don't do it. But let's say this is a scientific experiment and has been approved by government officials, okay? Which of the following statements are true? Select all that apply. So we can select more than one. It's a select all problem. The cannon was fired from a height of 25 meters. Is that true? No, our cannon was fired from a height of what? 50 meters. So not true, we're not selecting it. Next box, the initial velocity of the projectile was 4.9 meters per second squared. So can we see velocity from the graph? Can we tell what the velocity is? No. But it's saying our initial velocity was 4.9 meters. What? It's likely. Doesn't 4.9 tell us about the gravitation, the gravity? Not velocity, right? Right. Velocity has nothing to do, it's not the negative 4.9 or the negative 16, that's the gravity. And we can't look at the graph and tell what the velocity was. Okay, so we're not checking this one. We know it's in meters, and 4.9 is meters, but it doesn't say negative. But that's not talking about velocity, that's talking about the gravity. So negative 4.9 is gravity, not velocity, and we cannot determine the velocity just by looking at the graph from what we know at this moment. It took the projectile approximately 2.6 seconds to reach its maximum height. Is that true? Yeah, right here. Look at your vertex. At approximately 2.55 seconds, which that's approximately 2.6, it reaches a maximum height of 81.89. So yes, we will select that one. The maximum height of the projectile was 50 feet. Is that true? No, we just said the maximum height of the projectile was 81.89 feet. So that's not true. It took the projectile approximately 6.6 seconds to hit the ground. True or not true? True, and it says approximately, so it doesn't have to say 6.64, it says approximately. That is true. Everybody cool with that one? Anybody have questions, comments, or concerns? Okay, now the back side of this actually goes with factoring. We've already done factoring. We're not using the back side of this page from the workbook, okay? So that is your whole thing of notes. Your assignment is from the practice book. Those pages that you tore out from the practice book, and that was pages 63 through 66. I believe page 66 goes with a different section. So y'all only have to do, so 63, that's not a page to do, that's just fine. You have to do page 64 and 65, 1 through 7, all parts. I know that looks like a lot, but how fast do we answer those questions? Okay, so it's not a big deal. Most of you will finish and turn it in before you leave today. 64 and 65, 1 through 7, all parts. If you're at home, I will post that on Schoology. And I'm stopping my video. If you did not finish your test though, put everything away because you're going to finish your test. Everyone else can work on the homework. Once you finish your test, then you can work on the homework.